Welcome to OB's Math e-Pathshala.
Today's topic is prime ideals in rings. Our next example uh, show that the ideal x square plus 1 in Rx is maximal. The ideal x square plus 1 in Rx is maximal. So it should be noted that x square plus 1 is irreducible over R. What we have already noticed that x square plus 1 is irreducible over R since it has no real solution. Since it has no real solution. So this polynomial is irreducible over the field of reals, and for that reason the quotient ring Rx by the ideal generated by x square plus 1 is a field. This is a field. And since it is a field, so this ideal, so it is maximal, and also since it is a field, so it is an integral domain, so it is prime. So thus we have observed that remark in a commutative ring with unity 1, commutative ring R with unity 1, if so if for an ideal M of R which is maximal, then from our known theorem R by M is a field, and for being a field R by M is an integral domain in particular. Which implies that since R by M is an integral domain, so this implies that M is a prime ideal. So this is another way of proving that in a commutative ring with unity 1, a maximal ideal is prime. So this is another way you can look at the proof of this theorem. That is, every maximal ideal is prime. So using the theorem that M is maximal if and only if the quotient ring is filled, so you can also prove that every maximal ideal is prime in a commutative ring with unity 1. Okay. Another example, let us have a look. Let us denote C01. It is a ring of all real valued continuous functions over a closed interval 0, 1. That is the ring of all real valued continuous functions over the interval 0, 1. Let A belongs to the closed interval 0, 1. Then define a set indexed by A, that is MA, defined by set of all those functions from the ring 0, 1 which will have a root at A, that is fa is 0. All those functions f belongs to C0, 1, fa equals to 0. So we would like to show that, so we claim that MA is maximal. MA is maximal. So for this we need to define a map capital F colon C0, 1 to the real number set by capital F of small f equals to f at A for all f belongs to C0, 1. So with respect to this point, we are evaluating each function at A. So this is the map we are looking for. Now our intention is to show that the defined map is a ring homomorphism. And once we show that this is a ring homomorphism, then using the first isomorphism theorem for rings, we can show that C0, 1 by the kernel is isomorphic to R. And then R being a field, it will imply that the quotient ring C0, 1 by the kernel is a field. And if the quotient ring is a field, then the ideal must be maximal. And then we show that this kernel is the set MA. So we shall move step by step. So firstly we show that capital F is a ring homomorphism. So for f g belongs to C0, 1, just considering two elements f and g, we will have capital F plus g, so it will evaluate at A, that is fa plus ga, that is capital F capital F g, and capital F fg equals to fga, that is fa ga, and therefore it is capital F of small f and capital F of small g, and this proves that capital F is a ring homomorphism. Now by the definition, capital F is onto. Why? What is the reason for that capital F is onto? Because for any real C belongs to R, we can define the constant map which is fx equals to C for all x belongs to closed interval 0, 1. And this implies capital F of, so in particular, FA equal to C. Now what is FA? FA means capital F of small f. So this is C. So for any real C, there exists a f which is mapped to C. And for that reason, capital F is onto. So capital F is an epimorphism from C01 onto R. So therefore, by first isomorphism theorem, so C01 by kernel of capital F is isomorphic to R. Now what is kernel of F? Set of all those F belongs to C01 for which capital F of small f is going to be 0. That is, set of all those functions, real valued continuous functions over 0, 1, which vanishes at A. And this is the set MA, what we have defined in the problem. So therefore, hence C01 by MA is isomorphic to R. And so R being a field, the quotient ring C01 by MA is a field, and hence MA must be a maximal ideal. So in this way, we can prove that for any real A belongs to the closed interval 0, 1, MA is a maximal ideal. So corresponding to each point in 0, 1 closed interval, we can correspond a maximal ideal MA. So another problem must pose that in the ring capital R is A, B, 0, 0, A comma B belongs to R, show that capital I equal to 0, B, 0, 0, B belongs to R is a maximal ideal in R. So you should keep in mind that whenever you are going to show some ideal is maximal, so it's better to define a map through which you can show that some suitable quotient ring is a field, like the way we have done for. So this is a trick that you need to define a map which will help you to show that a quotient ring is a field by using a first isomorphism theorem. So in this problem also, you can define a map in this way. You can define a map that is okay. phi colon the ring is R to a suitable set F. Now what is F? This is your choice. This is the trick, that here we will assume that F is A000, where A belongs to capital R. Now, with respect to matrix addition and multiplication, you can show that this F is a ring. And not only that, this F actually, it is a field. So it is your job is to show that F is a field. So this is your task. That you need to show that F is a field. And we are considering a map phi from R to F by defined by phi of, so the elements of R is AB00, that is AB00, and it will go to A000. Now it is very much easy to show that. It can be easily checked that so do it on your own. Check that phi is a ring homomorphism from R onto the field F, and therefore by using first isomorphism theorem, R by kernel of phi is isomorphic to F. Now what is kernel of phi? You may check that kernel of phi is equal to the set of all those matrices of this form 0b 0 b belongs to R, and which is nothing but what we have desired, that is I. So this kernel is equals to I, and hence R by I is isomorphic to F. Now since F is a field, so R by I is a field, and this concludes that I is maximal. So in this way, so this is an important way of proving an ideal is maximal. So you need to consider the domain set. So this is your choice, this is your wiseness, that you need to consider a suitable choice of fields or integral domains. So that depends on what you are trying to prove, whether it is prime ideal, whether it is maximal ideal. So it is your choice to choose a particular field or an integral domain to prove that the ideal given in your problem is maximal or prime. Yes. So this is an important way of proof. Yeah. And it should be remarked that it should be remarked that this F is another kind of representations of real numbers. Through the correspondence, that is, we can make a remark that one can establish the correspondence between F and R, phi from F to R, by the natural correspondence, which is A. That is, phi of A0, 0, 0 is A. And it can be easily checked that this phi is a 1-1 homomorphism from F onto R. So check on your own that phi is a 1-1 homomorphism from F onto R. That is, capital F is isomorphic to actually capital R. So in this way, you can also show that F is a field. So this is another way of proof. And preliminary way will be by showing that every non-zero element in F has a multiplicative inverse. So that is elementary. Also, it should be observed that in this problem, this one, the ring R that we have considered doesn't have unity. So also it should be observed that the ring R doesn't possess any unity, doesn't have unity. Although the quotient ring R by I has the unity 1, 0, 0, 0 plus capital I, this quotient. The R doesn't have any unity, but its quotient ring R by I possesses the unity 1, 0, 0, 0 plus I. So one can prove that actually for a commutative ring R, if M be an ideal of R and R by M is a field, then M must be maximal. So that is, this example actually gives us that for a commutative ring R, and considering an ideal, M be an ideal of R, such that the quotient ring is a field, then we must have capital M must be maximal. So must be maximal. The key point is that R by M does not contain any non-zero proper ideals for being a field. Since in any field you cannot have any non-zero proper ideals. So this is your key point to prove this.
Thanks for watching. Please subscribe, like and share.